Hello everyone. Now our group will present about PFAS contamination in drinking water.
PFAS pollution in drinking water is a growing concern due to potential health risks associated with exposure to these synthetic compounds. PFAS are used in a wide variety of industrial and consumer products and can enter the environment from a number of different sources. Contamination of drinking water sources with PFAS may be challenging to find and address. This problem might be raised in the public's consciousness, potential risks could be explained, and contamination prevention strategies. Next, the issue of PFAS contamination in drinking water needs to be resolved due to the potential health risks associated with exposure to these chemicals. PFAS have been linked to a number of health problems, including developmental delays, liver damage, and an increased risk of some malignancies. PFAS pollution also can be difficult to detect and remediate since these chemicals can enter the environment through a variety of sources and can travel considerable distances in water sources. This implies that contamination, even at low levels, may be difficult to find and remove.
Next, methods. PFAS can be isolated from water samples using solid phase extraction (SPE), liquid-liquid extraction (LLE), or solid phase microextraction (SPME). SPE offers high selectivity, sensitivity, versatility, and compatibility with various sample volumes, while LLE is widely used for environmental monitoring, research, and regulatory compliance monitoring. Moreover, LLE is a simple extraction method for water, soil, and biological samples, but has limitations like low selectivity and large organic solvent volumes. SPME, a similar method, uses a fiber coated with a solid phase sorbent material for PFAS compounds. And finally, SPME is useful for rapid screening, environmental monitoring, and field sampling, but has limited capacity and selectivity for trace level PFAS compounds.
So now we will discuss the different chromatography techniques that can be used to analyze PFAS in water samples. PFAS in water samples can be examined using a variety of chromatographic methods. The first one is liquid chromatography. This method divides PFAS molecules according to their chemical characteristics and enables the identification and measurement of certain PFAS compounds in a water sample. Liquid chromatography is a method for separating and analyzing mixture components based on their chemical characteristics. According to the fundamental tenets of LC, the sample to be examined is dissolved in a liquid and it is then transported through a column that is filled with a stationary phase. Stationary phase is intended to selectively keep some elements of the sample while allowing others to move through more quickly. Based on how they interact with the stationary phase as the sample moves along the column, the various components are separated. Strongly retained components go through the column more slowly than less strongly retained ones, which move through the column more quickly. Now we move to advantages of LC. LC have high sensitivity, high selectivity, flexibility, and can be automated. The limitation of LC is LC has limited resolution, small sample size, complexity, and LC also can be expensive. The second one is gas chromatography. It is to examine volatile PFAS chemicals in water samples. GC is frequently combined with mass spectrometry. For GC principle, the technique of gas chromatography is used to separate and examine the constituents of a mixture according to their chemical characteristics. The analysis sample is first vaporized and then passed through a column containing a stationary phase, according to the fundamental principle of GC. A substance called the stationary phase is intended to selectively keep some elements of the sample while allowing others to move through more quickly. Based on how they interact with the stationary phase as the sample moves along the column, the various components are separated. Strongly retained components go through the column more slowly than less strongly retained ones, which move through the column more quickly. A detector at the column's end then finds the separated components and produces a signal that is proportionate to the amount of each component present. After that, the signal is examined to determine the sample's various components. The advantages of GC is GC have high sensitivity, high resolution, flexibility, automation, and quickness. The limitation of GC is GC requires a sizable sample size. It can only analyze volatile and semi-volatile substances. GC is a potentially complicated approach that calls for specialized tools and a knowledge to execute and analyze the outcomes. GC can be expensive, and the significant sample preparation required for GC can be labor and time intensive. Next is ion chromatography. PFAS compounds can be divided and analyzed using IC based on their ionic characteristics. Overall, the sensitivity and precision needed for the study, as well as the specific PFAS chemicals being analyzed, will determine which chromatographic approach is best. Next, ion chromatography is a method for separating and examining ions in a sample according to their charge and chemical makeup. According to the fundamental tenets of IC, the material to be examined is dissolved in a liquid, and then it is transported through a column that is filled with a stationary phase. A substance known as the stationary phase is intended to selectively keep some ions from the sample while allowing others to pass through more quickly. Based on how they interact with the stationary phase as the sample moves through the column, the various ions are sorted as it does so. Strongly retained components go through the column more slowly than less strongly retained ones, which move through the column more quickly. An end-of-column detector that detects the separated ions produces a signal that is proportional to the concentration of each individual ion in the sample. The various ions in the sample are then determined by analyzing the signal. The advantages of IC is IC can identify particular ions in a sample by separating ions according to their size and charge. IC also is an effective instrument for trace analysis. Inorganic and organic ions, as well as more complicated biomolecules, can be analyzed using IC. IC also can be automated. The limitation of IC is IC has limited resolution, small sample size, potentially complicated technique that calls for specialized tools and knowledge to execute and comprehend the findings, and IC also can be pricey.
PFAS contamination in drinking water is a global concern, with high levels detected in 2019 in the Selangor River and in 2012 at the Langat River. Authorities have implemented measures like temporary water supply, treatment upgrades, regulatory measures, public awareness campaigns, and long-term monitoring. A combination of scientific investigation, regulatory action, and community involvement is crucial for ensuring water supply safety. Malaysia's Selangor River and Langat River face safety concern due to PFAS contamination from industrial activities including waste disposal, affecting both domestic and industrial water supply.
Let's talk about the prevention first. Firstly, controlling the use of PFAS chemicals. To stop PFAS chemicals from contaminating the environment, governments can control their production and usage. This may involve imposing limitations on the production, import, and use of goods containing PFAS. Secondly, safe disposal of products containing PFAS. To avoid contaminating water sources, products containing PFAS such as firefighting foam should be disposed of safely. This may need treatment at specialist facilities or cremation. Thirdly, regularly checking for PFAS contamination in water sources. It can help to spot potential sources of contamination and reduce exposure. This may involve keeping an eye on drinking water sources, surface water, and groundwater. Fourthly, use of substitute products. Using substitute goods devoid of PFAS can assist in preventing water sources stain. For instance, ceramic or cast iron cookware can be used in place of non-stick cookware, and PFAS-free firefighting foam can be used in place of non-stick firefighting foam. Lastly, safeguarding water resources. Restricting land use and limiting runoff can shield water resources from contamination and help stop the PFAS from entering the water supply. The use of fertilizers and pesticides can be restricted, stormwater runoff can be managed, and wetlands and other sensitive areas can be protected, among other things. Next is remediation. Firstly, granular activated carbon GAC filtration. GAC filters are good at removing PFAS from drinking water. This process includes running water over a bed of activated carbon, which allows the PFAS to adhere to its surface. To keep them functioning properly, the GAC filters must be often updated. Secondly, ion exchange. Ion exchange resins can also be used to eliminate PFAS from drinking water. The PFAS ions are switched out for other ions that are bonded to the resin by passing the water through a bed of resin in this process. To keep the resin working properly, it must be routinely replenished. Thirdly, reverse osmosis (RO). By pushing water across a semi-permeable membrane that traps PFAS molecules, reverse osmosis membranes can remove PFAS from drinking water. Although costly, this approach is efficient. Fourthly, electrochemical oxidation. Using electrochemical oxidation, PFAS molecules can be converted into less dangerous compounds. By running an electric current through the water, this technique creates reactive species that can oxidize PFAS. Last but not least, treatment of the soil and groundwater. The source of the contamination can also be used to address PFAS pollution. Techniques like bioremediation, chemical oxidation, or heat treatment may be used for this.
Lastly, conclusion. In conclusion, it is important to note that PFAS contamination is not limited to Malaysia. Similar cases have been reported in various countries, including the United States, Australia, and Europe. In each instance, a combination of scientific investigation, regulatory action, and community involvement has been crucial in identifying and addressing the contamination to ensure the safety of drinking water supplies. Safe water means safe environment for humans to live. Therefore, all parties involved need to do their parts in maintaining the safety of our drinking water to ensure humans' well-being. That's all from our group. Thank you.